Hello ladies and gentlemen, we're going to do 1.4 to 1.5 today. We're going to discuss continuity, one-sided limits, the intermediate value theorem, and infinite limits. So I won't read your objectives for you because they're sitting right there. And your title kind of says it all anyway, but there you have it. Today's video is shorter, lucky you. So let's start with section 1.4, and we're going to talk about continuity. So if you'll remember, continuous means that there are no breaks in a graph, there are no holes, there are no jumps. Okay? There are three criteria for continuity. So we're going to kind of talk about the criteria in terms of the definition. So a function is continuous if, one, f of a constant value, so some x value, is defined. Two, and this is part of our criteria, that the limit of the function as x approaches c exists. Okay? And then the last one, the last criteria for continuity would be that the limit of the function as x approaches c is actually a defined value. So the limit has to exist and it has to be approaching a defined value. Okay? And then a statement that's kind of a does statement, but it's still important to think about, is that a function is continuous on an open interval if it is continuous at each point in the interval. So much writing. Alrighty, for discontinuity. So obviously, discontinuity, sorry, I'm thinking of the word discontinuous and trying to spell discontinuity. So discontinuity is going to be a break in the graph. Remember, I can classify discontinuity by one of two types. It can either be removable. So removable discontinuity, and we're actually going to talk about removable discontinuity in terms of limits, but it can potentially be removed through factoring. So I can factor and then maybe remove. Okay? Non-removable is going to create a hole in our graph. Okay? Oops, I'm sorry. This one is the one that's going to create a hole. So even though I remove it, it creates a hole in the graph. Non-removable discontinuity cannot be removed mathematically. So that means that even if I factor, it might not be possible to remove that factor. And it also is going to create a vertical asymptote. Okay, so remember VA is shorthand for a vertical asymptote. So let's do a quick little example where we want to discuss continuity. So I want to discuss continuity. And remember, anytime you're told to discuss, that means you have the burden of proof and you want to give some information about the continuity of the graph. All right? I'm just going to draw the graph because we know what this guy looks like, and so he's got a branch here and a branch here. Well, I know that the function is undefined at 0, so I can say that the domain of the function is a negative 0 to 0, and then it starts again and goes from 0 to positive infinity. Okay? I need to talk about and classify the type of discontinuity, so I have non-removable discontinuity. And since I've defined the domain, I can actually say that the function is continuous over the domain, but I can't make that statement unless I've actually defined the domain. Okay? And if I didn't want to make this statement, I could also say that the function is discontinuous at x is equal to 0. So those are my possibilities as well. All right, so let's talk about one-sided limits now. Okay, and I'm going to do that by talking about the square root function. So let's say I have y is equal to the square root of x. Well, I can talk about the limit of the function as x approaches 0 from the right, and I would get the value 0. But I can't talk about the limit of the function as x approaches 0 from the left because there's nothing over here. Therefore, that limit doesn't exist. So this would be what we would consider a one-sided limit. The limit only exists if I come in from the right. So let's consider another kind of graph. We did several of these last year, and so it's kind of entertaining. So I'm going to consider the function as x approaches a negative 2 from the right, and my function is going to be 4 minus x squared. Well, it turns out that this is the top half of a circle. So here's a negative 2 and a positive 2, because remember, I could rearrange the function, put it in an order I'm used to seeing, okay? And it's going to look like that. So there's the top half of my circle. Well, as I approach the negative 2 from the right, then I would say the limit of the function as x approaches a negative 2 from the right is 0. But what would happen if I tried to take the limit of the function as x approaches a negative 2 from the left? Well, as I come into a negative 2 from the left, there's nothing there, so that limit doesn't exist. So again, you can see that there are cases where I have to do a one-sided limit. So here's something interesting to think about. Interesting to think about. If a limit exists at a point of discontinuity, then you have confirmed that the discontinuity was removable. It's actually kind of an interesting thing to think about. If a limit exists at a point of discontinuity, then you have confirmed that the limit was removable. So let's do an example to illustrate that. So let's say I want to do the limit as x approaches 6 of x minus 6 over x squared minus 36. I can't just substitute in and then do my direct substitution because I get the indeterminate form, so I'm going to do some rewriting. So this is the limit as x approaches 6, and I have x minus 6 over x plus 6 and x minus 6. Well, these remove, right, because I can with factoring. So then I get the limit as x approaches 6 of 1 over x plus 6. The indeterminate form has been removed. Now I can do direct substitution, and so I get a limit of 1 over 12. So what we just said is if a limit exists at a point of discontinuity, I have 2 points of discontinuity, one at x plus 6 and one at x minus 6. Well, because I could find the limit and get a 1 over 12, then I can confirm that I have removable discontinuity at x is equal to 6. So this would be my removable discontinuity. Well, and then if I look at my graph, I have a vertical asymptote, or I don't have to look at the graph, I can just look at my equation, that x is a negative 6, and this is non-removable because it wouldn't factor out discontinuity. Alrighty, so that's actually an interesting fact to consider. Okay, so let's talk about now what happens when I put functions together and I want to talk about their continuity. So I'm going to talk about continuity. And what happens if I have a function that looks like this, x plus the sine of x? Well, let's put this in our calculator and graph it, because we can. So if I put this in my handy-dandy calculator, remember that I can't graph a trig function unless I am in radians. So I'm going to graph x plus the sine, there it is, of x. And I'm going to do a zoom 7, which is zoom trig. Ooh, the glare is bad. I need to move it over here. Okay? And if we look at the graph, we can see that it's continuous, but let's talk about a way to justify that. So I know that f of x is equal to x is continuous over all reals, because domain is all reals. And then if I take this piece, f of x is equal to the sine of x, well, this is also continuous over all reals. Well, if I put the two together, if it's continuous over all reals for both, the continuity is the intersection of each of the individual continuities. So I'm going to put the intersection of the individual continuities. Then we could show that f of x is continuous over its domain, and that happens to be the real numbers. Okay? All right. So now let's talk about another situation that deals with continuity, and let's talk about a composite function or a composition. So let's say I have a function that's f of g of x, and when I want to address its continuity, well, if I know that g is continuous at c, and I know that f is continuous at c, then I would know that f of g of x, the composition, is going to be continuous at c. Alrighty? Alright, let's do an example. And we are going to discuss the continuity of a piecewise. And this is going to be the sine of 1 over x, and x can't equal 0, and then 0, and x does equal 0. Alrighty? So we're going to discuss the continuity, and remember this is called a piecewise function. And I know you know that because we've been together for 3 years. So first off, let me go back and remind you how to enter a piecewise in your calculator. There's a couple of different ways you can do it. So I'm going to clear this. In my opinion, the easiest way is to think about this is a point discontinuity for the graph. So if I take the function and divide it by its point of discontinuity, then it's going to have an open portion of the graph. So I'm going to enter my function as the sine of, remember it has to be in parentheses, 1 divided by x, close, close. And then I'm going to divide it by where the graph is undefined. If that in my second test doesn't equal 0. Okay? And so that would be my first piece. The second piece, it has to be in parentheses, and I'm going to divide it by the point where the graph is defined, and then that would create what I need. Sorry, brain and mouth aren't working together. And I'm going to do a zoom 6, because it's really kind of cool looking. But I really can't see things as well. Oops. Let me see where I made my mistake. Y equals, oh, there it is, my bad. So we're going to go in and insert the 0, because I forgot that little guy. We're going to graph him again. Whew! And in case you didn't know that, when you get an error and it tells you 1 quit or 2 go to, if you put in the 2 go to, it usually tells you where you screwed up, which is kind of nice. This is difficult to see, so I'm just going to do a zoom box and just kind of reminding you of some of the things that we can do. And I know you guys are usually better at your calculators than I am, but we're going to pretend that I know more than you do, so we're going to put that in. All right, so there's our first function, nice oscillating behavior. And it's still really difficult to see, but in this one, x can't equal 0, so there's a hole. But in this one, it fills the hole. Alrighty? So, let's talk about and break this into its individual components. So if I had y is equal to 1 over x can't equal 0, so its domain would be from a negative infinity to 0, unioned with 0 to positive infinity. Well, if I look at y is equal to the sine of x, this one is continuous over the reals, okay, and that's, remember, a negative infinity to a positive infinity. And then if I break up my other graph, y is equal to 0, this one is continuous over the reals, negative infinity to positive infinity. My piecewise function is the intersection, so we would say when I intersect these three that my function is continuous from a negative infinity to 0 unioned with 0 to positive infinity. But if we think about open a hole, close a hole, then I would be tended to say that I have a continuous function over the reals. If you consider the piecewise function as a hole, this opened a hole, this filled a hole, therefore there's no longer a point of discontinuity, so we would say that the piecewise function is continuous over the reals. Alright, so the next thing I want to talk about is the intermediate value theorem, and we're going to go back and talk about it at its early inception, not what you used it for as the year progressed last year, but let's talk about it from its very beginnings. So the intermediate value theorem, if you'll remember, it is called an existence theorem because really all it does is it shows the existence of something. And the intermediate value theorem actually shows the existence of a 0. So here's basically what it says. If I have, let's just say I have a graph, and I have an interval a to b. Well, let's say I know that f of a is positive, and I know that f of b is negative. So that means the y values were up here, and then the y values are down here. So that the intermediate value theorem says somewhere in the interval from a to b, there is at least 1, 0. So I know it seems kind of weird. We did have some great uses for the intermediate value theorem later in the year, but for right now, all it is an existence theorem, and it just tells me that somewhere in that closed interval from A to B, there exists a 0. All right, so cruising right along, now we're going to be in section 1.5. So let's consider the graph of f of x is equal to 3 over x minus 2. I know from my pre-calc that I have a vertical asymptote at x is equal to 2. The numerator is positive, 1, 2. Ready? So I know that I have a vertical asymptote here, and I know that I have a horizontal asymptote, just stick that on here, at y is equal to 0 because the degree in the denominator is higher. And there's my handy-dandy function. Okay? But let's say I want to consider the limit of the function as x approaches 2. Well, if I look at the function as x approaches 2 from the left, I'm going to get a negative infinity. And if I look at the function as x approaches 2 from the right, then I get a positive infinity. So I know that, remember, if a graph approaches negative infinity, I know that it decreases without bound. And I know if a function or a graph approaches positive infinity, it's going to increase without bound. The other cool thing to notice is that these are one-sided limits, because if I consider the limit as x approaches 2 as a whole, it does not exist. But the one-sided limits do exist. The other cool thing to notice is now technically I have a vertical asymptote definition, and I'm going to write my definition in terms of a limit. So if a function approaches plus or minus infinity as x approaches c, okay, then the line x is equal to c is a vertical asymptote. So I think that's actually kind of interesting because it's a way of confirming a vertical asymptote. So if I take a limit as x approaches a constant, come in from the right and the left, and I get plus or minus infinity, or even plus infinity and plus infinity, then I know that I have a vertical asymptote. All right, let's do another example. And this is that true? Woo, this is true. This is your last example. Woohoo! This one says find the vertical asymptote and then verify using a limit. All right, we're going to be given the function f of x is equal to x squared minus 4, and I have x cubed plus 2x squared plus x plus 2. Well, the denominator appears to be fairly gnarly, but it's actually not as bad as it looks. I need to be able to reduce this, so I'm going to factor. The top is pretty easy. This is x plus 2 over x minus 2. It's just a difference of 2 squares. This guy is a quadnomial, looks yucky, so I'm going to do some grouping. So I'm going to factor out an x squared, and I'm going to get x plus 2, and then I have an x plus 2. So then if I rewrite, the top is going to stay the same for a moment. And then down here, I can factor out an x plus 2, and I get left with an x squared plus 1. The x plus 2's cancel. I have removable discontinuity. Remember, that would mean that the limit would approach a specific value, and we could find that value. Right here, I have, if I solved that, I would get x squared equals a negative 1, x is equal to plus or minus I. Because imaginary numbers don't show up on our real number plane, then to answer the question, I have no vertical asymptotes. And I'm going to confirm that with a limit. So I'm going to take my limit from my newer, I couldn't think of a word, sorry, of my newer thing. So I'm going to approach a negative 2, okay? Did I do something wrong? I did. My bad. I have a hole at x is equal to a negative 2, okay? Alrighty, so I don't have a vertical asymptote because we removed it, but I do have a hole there. So let's take the limit of the function, and I'm going to have x minus 2 over x squared plus 1, and we're going to approach as x approaches a negative 2. Because if I get infinities, then I know that I have a vertical asymptote. If I get a value, then I know that I have removable discontinuity. So if I do my direct substitution, I'm going to get a negative 2 minus 2 over a negative 2 squared plus 1. So sorry, I'm going to come down here. I'm going to get a negative 4 over 4 plus 1 is 5. I got a specific value, which confirms that I have removable discontinuity. This is an imaginary number, so I have confirmed my answer that there were no vertical asymptotes, because a removable value does not make a vertical asymptote. And when I got a specific value from my limit, it confirms that I have a hole resulting from removable discontinuity. Alrighty, that's it for the day. I will see you tomorrow. And interesting enough, ladies and gentlemen, Chapter 1 is over.